Hello. So, in this last module, what we are going to discuss is flow in pipes. If you go to any chemical process industry, the first thing probably you will notice that the industry has a number of pipes, and when the say crude oil needs to be transported from the production site where the oil is being drilled and being brought to the surface, it needs to be transported to the refineries, and then further on it needs to be transported to from the refineries to the distribution site. Sometimes it may happen via trucks, and at other times it may happen the transportation of oil as well as say natural gas happens via pipelines. So, flow through pipeline is a very important topic for chemical engineers. Now, when we talk about say biomedical engineer, again the size of the pipes will vary. It may be of the order of few mm and few centimeters, but again the flow in pipes is important. There the flow will be a laminar. For example, when we talk about the cardiovascular network, you have different pipes starting from aorta, which is about 2.5 centimeter, to down to the capillaries, which are about say 10 microns or so. So, in each case you have network of pipes, and one of the requirements that we need to do say as an engineer to design the pumping system. So, when you need to design the pumping system, you need to know how much pumping power or how much head the pump should be able to provide. When I say head, how much pressure that the pump should be able to provide, that the losses that happen in the system they are overcome. So, that is a very important calculation, and the focus in this module actually will be on such things, especially the calculation of head loss in the pipes. So, if you take a typical piping network, you may have a pump which pushes the fluid through, and then it goes through, and you have a number of bends, etc. So, apart from bends, you will have say valves which may control the flow rate. You may have reducers and expanders where the pipe size is changing, say from 1/8 inch to you are getting to 1/4 inch or other way around. So, all these elements of the piping system we need to take into account and see what are the pressure losses in these elements. Okay. Now, we have done a bit of flow in pipes. We have looked at laminar fully developed flow in pipe and obtained a relationship for pressure drop in terms of flow rate, what we called Hagen-Poiseuille law. We also looked at turbulent flow in pipes, but for turbulent flow in pipe in the previous module, we looked at the velocity profile. We still do not know the or we have not discussed what is the pressure drop when the flow is turbulent in a pipe. So, all these things we will discuss. But even when talking about laminar flow, what we discussed is fully developed flow. So, before we talk about the pressure loss, we will just touch upon the topic of developing flow. So, if you have say a pipeline which is say the pipeline is in a river, then because you can consider the boundaries of the river are sufficiently far away, then the velocity in the middle of the river probably it will be turbulent in most of the cases, and when it is so, then the velocity at the entrance of the pipe will be uniform. So, the flow enter with a uniform velocity. Now, when it encounters the wall, when the fluid encounters the wall, the velocity at the wall needs to be 0 because of no slip boundary condition, and the boundary layers start developing on the wall of the pipe. And eventually what will happen, these boundary layers will grow, as we have seen flow over in the case of flow over a flat plate. And when these boundary layers grow, it will be, let us say you have a circular pipe, then boundary layer will grow on at each point on the say entrance. Now, these boundary layers will grow and then eventually they will merge. So, the point where the boundary layer cannot grow further is where you will have a fully developed flow, the velocity profile will be parabolic for a laminar fully developed flow. But before that, the length that is required, you call that length as developing length or entrance length. So, basically the entrance length or developing length, it is defined as the distance from the entrance of the pipe. So, in this case we can say that this length is what is entrance length or developing length. So, we will write this as L development. Now, if the flow is laminar, then you will have a different entrance length, and if the flow is turbulent, the entrance length will be different. So, for laminar flows, it has been observed that the development length is equal to 0.06 RED. This number you may find varying, you may find it say in some places it is 0.05, in some places you may find it 0.056. Okay. So, the development length, it depends on Reynolds number, and in non-dimensional term it is say you write is L by D for developing, or you can say if you want to find the length, then it will depend on the flow Reynolds number and the diameter. So, it is L by D is equal to 0.06 RE. If you consider the Reynolds number 2300, which we take as the limit when the flow above which the flow does not remain laminar anymore. So, the highest development length for a laminar flow is 2000 when we calculate it for Reynolds number 2300. So, if we substitute the values, we will get the entrance length of about 138 D. So, for Reynolds number when the flow is laminar, then the development length is about 138 diameters or 140 diameters. When we talk about turbulent flows, because there is lot of mixing in the transverse direction, you have eddies in turbulent flows, and that causes the flow to develop relatively faster when you compare with the laminar flow. And it has been observed that the turbulent velocity profile for the mean velocity, it develops within 25 to 40 pipe diameters. But other turbulent quantities such as say fluctuations, turbulent kinetic energy, etc., they take longer to develop, and it may take up to 80 pipe diameters or more to develop. So, these numbers give us an idea about how much length will be required for the flow to develop. Now, when we discussed Reynolds transport theorem and the integral analysis, we looked at apart from mass conservation, momentum conservation, we also looked at the energy conservation. So, we will go back to the energy conservation, and then there we applied the energy conservation for the piping system. So, we will do that again, or we will recall that. So, if we consider a steady flow through a piping system, we can take a simple pipe with a band. So, the flow is coming, let us say, at section 1 here, and it is going out at section 2. So, if we write down the energy conservation equation, so this is Q dot, which is the rate of heat transfer, heat being given to the system. So, we can consider a control volume here. So, this is my control volume. Q dot is the rate of heat input. W dot you could have shaft work, and the work due to the viscous stressage. So, the rate of work is that the work is being done by the fluid. So, you have that, and then you have rate of change in the energy, and when you write this from a system formulation to control volume formulation, you get this. You have the total internal energy of the system plus this flow work P by rho. So, if we consider the flow to be steady, then this term will go away, and again no shaft work, then this term will again will go away, and because the viscous shear stressage, the velocity at the boundaries of the control volume is 0. So, the viscous the work due to viscous shear stressage again will be 0. Now, that gives us a simpler relationship. You will have q dot, which is rate of heat exchange, that is equal to integral over the control surface E plus P by rho into rho V dot dA. Okay. And we can write E, the total energy of the system, in terms of U plus kinetic energy plus Gz. Remember, the U here is the internal energy, or we can say specific internal energy, because E is the specific total energy of the system. So, we can expand that, and then we can consider it for the entire control surface. So, when we do that, I would just like to emphasize again, because what we have been doing throughout the course is q dot is or we use q as the symbol for flow rate, volumetric flow rate, whereas here we use q dot, which is the rate of heat transfer, and we have been using small u as the component of velocity along the x direction, whereas u here is the specific internal energy of the fluid. So, if we write down this equation considering the control surface, then we will have the two surfaces, surface 1 and surface 2, where the velocities are not 0, and we can write down for each term, we can consider these. So, we have V dot dA coming into picture, and then rho together with it. So, because we want to, or we will know the volumetric flow rate or the mass flow rate. So, we will write this down in terms of mass flow rate. At location 1 or at the entrance, the V is pointing inward, the area vector is outward. So, we as we do usually, it will be minus rho V dA, and at the exit both of them will be pointing outward. So, it will be integral rho V dA. Now, with this we can substitute. So, the first term U is internal energy. So, we can say the internal energy at section U minus internal energy at section 2 and internal energy at section 1. So, U 2 minus U 1, from this we will get, and this is m dot, because m dot at 1 is negative. So, that is why we have got this minus sign here. Now, the next term we have this one. So, if we look at this term, again we can write this rho V dot dA, the pressure at section 1 and section 2, rho and P are we can say constant across the section, or we can take the average pressure. So, P 2 by rho minus P 1 by rho into m dot, again the minus sign because m dot is negative at the entrance or at section 1, and then we have the third term, which will be m dot into G Z 2 minus Z 1. So, we have looked at the three terms, and the only term left is this one. So, because it has V inside it, and when we consider, now we know that the velocity is not uniform inside a pipe. So, we will have the velocity varying across the cross section. So, we will not consider the what we have done is we are still having this inside the integral sign, because we will be varying across the area. However, this becomes inconvenient. So, what we could do, we could write velocity in terms of mean velocity. Okay. So, for turbulent flow, it will be the average of mean velocity for the turbulent flows and average velocity in the laminar flow. Okay. So, this can be done if we define a factor to take into account that we are taking the mean velocity in place of the actual velocity. So, what we could do is the term of the form v square by 2 rho v dA, we can write, because rho v dA will basically be m dot, and we can in place of v squared we can write v bar squared. So, when we write v bar, it will be constant throughout A. So, we will be able to take it out of the integral sign. So, we can write this as when we write this as v squared bar, we have brought in a factor which is called kinetic energy coefficient. Okay. So, we can bring in a kinetic energy coefficient and represent the velocity v in terms of the mean velocity v squared. So, this term then becomes alpha m dot into v squared by 2. So, that gives us the definition of kinetic energy coefficient. So, kinetic energy coefficient alpha is equal to integral over the area v cube. So, if we look at here, we can combine this. So, v cube rho dA divided by m dot, because rho v dA is m dot, into v squared by 2. So, that gives us kinetic energy coefficient. Now, if you substitute the values, you will find out, because we know what is the velocity profile or how the velocity profile changes for fully developed laminar flow, the parabolic velocity profile, and we can write area in terms of 2 pi r dr, dA is equal to 2 pi r dr. So, we will be able to calculate alpha for laminar fully developed flow, and you will notice that it comes out to be 2. I will leave that as an exercise for you to do. If you consider turbulent flow, then the quantity will be very close to 1. So, if you use say 1 by 7th power law, then the quantity will come somewhere around 1.06 or 1.07. So, we can generally take this value to be alpha is equal to 1. So, you need to remember that when you are solving the problems for turbulent flow, the kinetic energy coefficient is generally, or kinetic energy factor is it is called sometimes, it is generally taken to be 1. But when it is laminar flow, then it will not be 1, and you will need to take the value 2. Okay. So, with this we will be able to write or we will be able to eliminate this integral sign here. So, let us go back to our energy equation, and we will write this now by dividing m dot. So, we will write this in terms of q dot divided by m dot. So, q dot by m dot is equal to u 2 minus u 1, where u 2 minus u 1 is the change in internal energy, plus alpha 2 v 2 squared by 2 minus alpha 1 v 1 squared by 2, which is basically kinetic energy, g z 2 minus z 1 the potential energy due to gravity, and then you have p 2 minus p 1 by rho, which is basically the pressure or the change in pressure. So, if you remember, we have a 3 term familiar, the kinetic energy, potential energy and pressure, which we say that the change the sum of these 3 is constant along a streamline when we talk about Bernoulli's theorem, and the assumption was there that you should have an ideal fluid, the inviscid fluid. Now, if we consider the viscous fluid, so when you have viscosity, there will be friction at the walls. So, the friction comes into play. So, to take into account the losses due to friction, you have these two terms. So, we will rearrange these system, these equation. We can bring in q dot by m dot in here on this side, and this all come on the other side. So, we can write u 2 minus u 1 minus q dot by m dot. So, let us look at what is u 2 minus u 1 is basically, that is where u is when you call it c into t. So, basically when u is changing or when u is increasing, you will have the mechanical energy changing to thermal energy. So, because of frictional losses, the mechanical energy is going to change into thermal energy, and some of this energy may be lost because of the heat transfer. So, that is the total losses. If you consider, this gives you the total loss due to friction. And what is this? This is the mechanical energy we consider, P by rho plus alpha V 1 bar squared by 2 plus C Z 1. So, that is the mechanical energy at location 1 at the entrance, and that is the mechanical energy at location 2 at the exit. So, if we would have said that it is an ideal fluid, it is an inviscid fluid, then this term would have become 0 because the losses are negligible, and this would be equal to 0. So, you will say that this is the Bernoulli equation. Now, this is the Bernoulli equation, but with consideration or with taken into account the frictional losses. Okay. So, this term is basically what we call the total losses, or so total loss of mechanical energy per unit mass, because the unit that we represent in per unit mass, so energy per unit mass, it will be meter squared per second square. You can see it easily from here, G is meter per second square into meter. So, you have meter square per second square, and this is total losses. Now, it also is represented in terms of where the units are in terms of meter, as we have been looking at or we have been doing with the Bernoulli's equation. So, we can represent it as capital HLT. So, L represents here loss and capital T represents total. So, small h we will use when the units are in meter square per second square, and we call it loss in energy per unit mass. And when we represent it as in terms of capital H, the unit will be meter and we call it head loss. So, head HLT is equal to just this energy or the mechanical energy lost per unit mass divided by acceleration due to gravity. So, that will be our other form. So, now the question comes that if we have flow in pipes, we can use this very simple equation to find out the pressure requirements, P 2 minus P 1 we can calculate, or P 1 minus P 2 we can calculate that how much pressure or how much head needs to be given when you use a pump. So, which pump you need to choose. But the problem is that we do not still know what is head loss. So, now the question comes that what are these head losses. So, we can combine this, this should have been the head losses. So, we can combine this and say that the total head loss, they can be divided into two, major losses and minor losses. It is not necessarily that it is the major losses which is always greater, the magnitude of major losses is always greater, it is not necessary, it is the naming convention that we have. And so, major losses is basically the losses due to friction when you have a constant area pipes. So, we will discuss this in detail in the next slide. And then another is another category of losses is minor lossage. So, anything which does not come basically under this category, that lossage due to friction in constant area pipes, that will be covered in minor lossage. So, we think about we talked about developing flow. So, in the developing flow there will be the pressure lossage will not be same as in the fully developed flow. So, to take into account inlet and exits, it will be in minor lossage. Then we have reducers and expanders. When the diameter of the pipe is changing, it may change suddenly or it may change gradually. So, you will have a enlargement in the pipe diameter or a reduction in pipe diameter. So, the lossage at reducers and expanders will again come in minor lossage. Then you will have number of bends in your pipelines. So, the lossage at the bends will come in minor lossage, and you will have a number of valves and fittings, etc. So, those will also come under minor lossage. Okay. So, let us look at the major lossage. So, the major loss can be defined that if we consider a pipe of uniform cross sectional area. So, a straight pipe, the cross sectional area is constant, and we consider that this flow or this pipe is horizontal. So, when the pipe is horizontal, with all these assumptions we can write down the head loss equation. So, H L total is equal to P 1 by rho alpha 1 V 1 squared by 2 plus G Z 1 minus P 2 by rho plus alpha 2 V 2 squared by 2 plus G Z 2, in of course, this all in bracket here. Okay. So, when you say that it is a horizontal pipe, then basically Z 1 is equal to Z 2, and this will cancel out. When you say that the pipe is of constant cross sectional area, so area everywhere including at section 1 and 2 are equal. So, you will have A 1 V 1 is equal to A 2 V 2, and these will also cancel out. So, you will have H L total is equal to P 1 minus P 2 by rho. So, basically delta P by rho is head loss. So, remember the definition that head loss, even if a pipe network we talk about is having pipes of different cross sectional areas, the head loss is delta P by rho, because all the other things, for example, the change in cross sectional area will be taken into account in the minor lossage. So, that is my head loss, but when you look at the head loss, so say head loss in 1 inch diameter pipe and 2 inch diameter pipe needs to be calculated separately, because this will be dependent upon the diameter of the pipe. So, when we are talking about here, because it does not have, we consider that the flow is fully developed. So, there is no inlet or exit lossage. We are not looking at here any valves, any fittings, any reducers and expanders, because the cross sectional area is constant. So, there are no minor losses present. So, basically our total head loss in such case will be is equal to the major lossage delta P by rho. So, major loss is delta P by rho, which is the pressure drop per unit density. And so, this is the definition of head loss, and it does not include the gravity term. So, it is independent of pipe orientation. So, when you are looking at, even if the pipe is say vertical or inclined, it does not change. The major loss value does not change, because when you will be writing the energy equation, you will have a different term say Z 1 minus Z 2 to take into account for that. So, the major losses they do not depend on the pipe orientation. Now, we sort of know now that if the flow is laminar, pipe is of constant cross sectional area and the flow is fully developed, then in the laminar flow we can calculate major lossage. We have this Hagen-Poiseuille equation. So, we will be able to do that. But what we do not know is still how to do it for turbulent flows. So, let us discuss for turbulent flow. Now, because nothing we have learned until now for turbulent flows, there is no analytical solution that we could derive, and in the same way we will not be able to find the pressure drop also analytically like what we did for laminar flow. So, it is not possible, and when we could not do anything analytically, the best way is to look at the powerful tool of dimensional analysis. So, we could go back and see that what are the factors on this pressure drop through a pipe in turbulent flow might depend. And so, we can list down that the pressure drop may depend on the pipe geometry. So, pipe geometry, when we talk about, it may depend on the diameter of the pipe, as you see here. It may depend on the length of the pipe, as well as it may depend on the roughness of the pipe. So, we can write this roughness of the pipe in terms of small e here. Now, it can also depend, or it will depend on the properties of the fluid that is being used. So, it may depend on the viscosity of the fluid, it will depend on the density of the fluid. So, rho and mu come into picture, and then it will depend on the flow velocity. So, if we will take a mean or average flow velocity, let us say V bar. So, now we will have these, that delta P is a function of all these 6 quantities, and we can group them in dimensionless groups. What we could do is we can do the Buckingham pi theorem or use Gibson's method, or just by looking at the variables we can define the non-dimensional groups. So, if we take, let us say as rho, V bar and diameter as our repeating variables, then we can just see that what are the non-dimensional groups we can form. And we see here that there are 2 more quantities which have the dimensions of length. So, we can simply write them as L by D and E by D. So, 2 dimensionless groups we have already formed. Now, we have been doing dimensional analysis, and a very familiar dimensionless group we have is Reynolds number. So, we can define it as, say, rho V bar D by mu, or its reverse, depend on how do you do it. If you do Buckingham pi theorem analysis, then you will get as mu into rho minus 1 V bar minus 1 D minus 1, but what we are looking at is a dimensionless group. It is 1 over R e, or R e does not matter. Now, the last thing is we have covered all the dimensionless, all the dimensional quantities except delta P. So, when you non-dimensionalize delta P, you will see that you will have delta P by rho V bar square. So, that is the dimensionless groups, because we have been seeing, or we have been looking at, we can non-dimensionalize with the dynamic pressure with so pressure or delta P is non-dimensionalized by rho V square. So, we can write down that delta P by rho V square is a function of these other 3 non-dimensional groups or dimensionless groups. We said that delta P by rho is HL major, or we found that the major lossage is equal to delta P by rho. So, this term delta P by rho V square will be major lossage divided by V bar squared. Now, the experiments have shown that this is the head loss or major loss is directly proportional to L by D, because the dimensionless and dimensional analysis can give us the information that what are the relevant dimensionless or dimensionless groups, but we cannot find out from the dimensional analysis that what is the function or in what way they are related. So, now we need to go to the experimental data and try to see what relationship could be there. So, the experimental data has shown this that L by D is directly proportional to head lossage. So, we can write this the functional dependence in this form. You might see that we have changed this to, in the previous slide it was phi 1, because it was delta p by rho v squared. Then we could write this in terms of, because here we had 1 over r e. So, we have changed it to say phi 2, because we have changed it to r e here, and then again we have changed it to phi 3 because the function will change, but this is just to differentiate the functions. We still have that it is a function of r e by d. So, we will write this H L major divided by half rho v square, because half rho v square is what we call kinetic energy, and so kinetic energy per unit mass we can write as half v squared. So, H L major by half v squared is equal to L by d phi 4 into r e by d, again because we have divided by 1 by 2. So, the a different function. Now, this functional dependence, that this function depends on Reynolds number and the roughness factor E. So, this is grouped under a factor which we call friction factor or Darcy friction factor. So, Darcy friction factor we define as this is equal to phi 4 e by d, and that is H L major divided by half rho v square by L by d. So, we can bring in L by d in the denominator here. So, that is the definition of Darcy friction factor, and Darcy friction factor is a function of Reynolds number and L by d. So, we can write down or we can represent the major losses in terms of Darcy friction factor, taking into account that Darcy friction factor is the ratio of H L major divided by or divided by half v bar square L by d. Okay. So, if we write this in terms of H L major where it is in meter square per second square, then our definition will be this. If we write into capital H where the unit is in meter, then we will need to divide by g. So, v by v bar squared divided by 2 g. So, that is our definition of Darcy friction factor. Now, there is another friction factor that is defined, which is called Fanning friction factor, and it is just 1/4 of Darcy friction factor. The commonly used friction factor we have is Darcy friction factor, but every time we need to be careful that the friction factor that has been given is Darcy friction factor or Fanning friction factor. So, now we have defined, what we have done is we looked at that on what factors can delta p depend upon, and then we grouped all those in dimensionless groups. We used a bit of information from experimental analysis and said that this major losses is proportional to L by d, and then remaining function we have defined as Darcy friction factor, which is a function of R e and L by d. So, what now we need is what is f as a function of R e and L by d. So, if we know R e and L by d, if we know the pipe length, pipe diameter, fluid, so which will give us the density and viscosity and the velocity. So, we will, if we know the Reynolds number L by d, then can we calculate f? That is the question we will ask ourselves. Of course, we could do it for laminar flow, and we can rearrange the equation that is obtained for pressure drop in laminar flow. So, we know for laminar fully developed flow that the Hagen-Poiseuille law gives us that the pressure drop per unit length is equal to 128 mu q into pi d squared by 4, where q is volumetric flow rate. So, we can expand it, or we can write q in terms of mean velocity v bar into cross sectional area pi by 4 d squared. So, we will see there that pi and pi will cancel out and d squared will cancel out. So, we will have d squared remaining here. This will give us 32. So, we can write, because the major lossage is delta p by rho. So, we can find major lossage for laminar flow, that will be 32, and this L will go on the other side, on the right hand side. So, 32, and you have 2 d here. So, we will write 32 into L by d mu into V bar divided by one more d is remaining. So, d and we divided by delta p divided by rho. So, this rho comes in here. Now, we can rearrange it further, because we have mu V bar and d here and rho as well. So, we can try to arrange it in terms of a Reynolds number. So, what we have is a V bar missing. So, we can multiply by V bar here in the denominator and numerator. So, what we get is 64, because we have divided by 2 here. So, we will get this in terms of friction factor. So, there we have in the definition V squared by 2. So, when we divide by 2, we will have this at 64 into L by d mu by d rho V bar into V squared by 2. Okay. So, we can write this as 64 by Re into L by d into V squared by 2. And then now we bring in the definition of Darcy friction factor, which is HL major divided by V squared by 2 into L by d. So, we substitute this L by d V squared by 2, and the friction factor we will get is that F is equal to 64 by Re. So, for a laminar flow, F is equal to 64 by Re. When we talked about, or when we derived this relationship, we did not consider roughness factor, or we did not take roughness factor into consideration there, but the experiments show that for laminar flow, roughness does not come into picture, and F is 64 by Re even for rough pipes. So, roughness does not have an effect in the laminar flow in pipes. Now, the next question comes that what if the flow is turbulent? So, there is no functional dependence that one could obtain except by the experimental data. So, a very standard chart has been prepared, which is called Moody's diagram, and what it represents is the functional dependence of friction factor F as a function of Reynolds number and as a function of roughness factor. So, you can see this roughness factor is E by d here. Now, when the flow is laminar in this range, then you see a straight line, because the graph is log plot as you can see from the axis. So, the x axis is log and the y axis is also a log plot here. Okay. So, you see here that this is a straight line, and for laminar flow you have 64 by Re, it is independent of roughness factor. Suddenly, as the Reynolds number increases, so you see a sudden jump in the friction factor. Now, with the increase in Reynolds number in the turbulent regime, what you see is there are different lines, and you have the relative pipe roughness or E by d values given here. So, depending on the roughness factor, you will need to follow different curves. You can see that at higher values of roughness, the friction factor becomes independent of Reynolds number very early. Even at low values of roughness, say of roughness of 10 raised to the power minus 4, eventually at a Reynolds number higher than 10 raised to the power, say 3 10 raised to the power 6 here, it becomes independent of Reynolds number. And so, the question comes, why do we have the friction factor having a jump here? And the question or the answer lies in the velocity profile. So, if we define the velocity profile on a laminar flow and if turbulent flow. So, this is for laminar flow and this is for turbulent flow. So, you have a very thin viscous sublayer and the velocity profile is fuller. So, the gradient is larger as well as, so in the turbulent flows. So, the wall shear stress is going to be high and that is why you have high major losses and as a result friction factors are larger in the turbulent flows. Now, the next question, that why we have roughness effect in turbulent flows, but not in laminar flows. So, if we look at in the turbulent flows, we discussed that in the turbulent flow near the wall we have a viscous sublayer and these viscous sublayers will be very thin. Higher the Reynolds number, thinner the viscous sublayer is going to be. So, if that is the case, then when you have the rough pipes, then the roughness factor or this might be the viscous sublayer can be within the of the order of roughness. So, this could cause lot of disruptions. So, that is why the roughness has an effect in the turbulent flows. Now, if we summarize the Moody's plot, so we can say that laminar flow in pipes, it is a function of Reynolds number only and not on the roughness factor. It decreases with increase in RE for laminar flow, 64 by RE we have seen, and then there is a sharp increase here in transition, and in turbulent flows depending on the roughness is decreases gradually and then it becomes constant at the higher Reynolds number values. And this curves has been prepared with a lot of experimental data and appears to be quite accurate within plus minus 10%. Okay. So, that this curve could be used to find or to calculate, but if you want to code it, if you want to say write a code for major losses in a pipeline, then it will be easier to use some algebraic relationship. So, few algebraic relationship we already have for laminar flow. For turbulent flow, few algebraic relationships have been developed which represent Moody's chart or friction factor. So, one that is developed by Colebrook is used quite generally. So, that is 1 over square root of friction factor is equal to minus 2 log, it is log base E. So, this is E by D divided by 3.7 plus 2.51 divided by RE square root F. Now, if we know RE, if we know the flow Reynolds number, if we know the roughness of the pipe, then we can see that this equation is explicit. So, by explicit we mean that you have F in the left hand side and you also have F on the right hand side, and you cannot separate those, that you can bring both of them on one side because you have a log here. So, what we will need to do, we need to solve it iteratively. We will need to assume a value initially that let us say F is equal to 0.1 and then find what is the new value of F and do this again and again until we reach the value of F, that the value we guessed, that start of calculation and the value that we find after the calculation, they are not very different. So, it has been shown, or it if you do the calculations using different values, that even in any case you reach to a fairly accurate value which is up to 3 significant figures, up to 3 places of decimal, within few iterations you get this value accurately. And as a guide you could use F is equal to 0.1 as an initial guess which can help you in converging faster. The Colebrook relationship is slightly difficult in terms of that we need to solve it iteratively, and so Holland equation is another one, and in this it's an approximation of Colebrook equation, but there is no implicit behavior like we do not need to solve it iteratively. So, we could calculate if we know the value of Reynolds number and if we know the value of E by D, then we can calculate it directly using this equation. Okay. All these take into account the E by D roughness factor, but if the pipe is smooth, then using the relationships from the Blasius correlation, which is F is equal to 0.316 divided by Reynolds to the power 0.25. So, this is a simpler correlationship and it can be used for smooth pipes. Okay. So, what we have discussed in summary today is that we have looked at the developing flow first, that what is developing flow and what are the development lengths for laminar as well as turbulent pipes. For laminar flows, we said that L by D is equal to 0.6 R E, and for turbulent flows, the flow tends to develop, the mean velocity profiles tends to develop between 25 to 40 D, and the other turbulent quantities may take up to 80 diameter or so. Then we looked at the head losses, that how we can calculate. Using the energy equation and Reynolds transport theorem, we derived the Bernoulli's equation in a form where we also have the frictional losses or the head losses, and then we defined that what could be the different types of losses, major losses and minor losses, and we looked at then what is major loss. So, we said that major loss is basically the loss for fully developed flow in a pipe of constant cross sectional area and horizontal pipe. So, that way we define that H L major or the major loss is equal to delta P by rho, and from that we defined Darcy friction factor or Fanning friction factor, and the values of friction factor F is equal to 64 by R E for laminar flow, and the relationships or the Moody chart for F in turbulent flow. Okay. So, we will stop here, and in the next class we will discuss the minor losses, etc. Okay. Thank you.